Alright, welcome back. Now, we're going to talk quite a bit more about quantifying turbulence and so on, and measuring turbulence in the rest of the lectures of this module. But before we get too far with all that thing, why do we care? Why would we care about turbulence? And broadly speaking, your book's going to throw three kinds of answers at us here. It's going to say that it's about turbulent load on wind turbines. It's going to be about how certain kinds of clouds are formed, and it's going to be about certain fluxes at the surface of the Earth. The business of turbulent load is really the one that's most directly relevant in the business of wind energy. Turbulent load tells us that turbulence is not really what wind turbines and all their parts can be engineered to withstand. The actual workings of the turbine itself are sort of engineered around like a constant force acting on them at a given wind speed, not continuously being buffeted by the passing of these eddies. You can well picture how as each eddy goes past, say, a wind turbine, it exerts torques on the blades and on the bearings and so on that is difficult to design for, and produces wear and tear on the moving parts of the wind turbine. And your book actually provides some information there about like the different ratings for different turbines. In the purpose of my class, I wouldn't ask you questions about like the different ratings and so on. But if, maintenance of wind turbines is the direction you wanted to go on a career path, you might want to review how, there are different standards for like the amount of turbulent load that a given turbine can withstand. From a more meteorological perspective, a very important feature about turbulence in the atmosphere is that certain types of clouds are produced by turbulence. And I actually have a lot of different examples I could give of this, but I think for the purposes of today, what I like is this aerial photograph here looking down on a layer of mid-level clouds in the atmosphere. These clouds are, I don't know, maybe 4 or 5 kilometers above the ground or something like that. They're a layer of clouds, and for the purposes of what I want to do here, I'm going to show you how these clouds are going to be formed by dynamic instability and the production of turbulence in the atmosphere. Now, I had a really hard time getting this drawn well, but picture that that black arrow there is like the winds below that cloud layer. And they're a certain strength, let's say not all that strong. Whereas like above the cloud layer, the winds are stronger. Okay, you see what I'm trying to illustrate there with that black and red arrow? The winds are getting stronger with respect to height across that cloud layer here. There is a wind shear, a change in U with respect to Z. Okay, well, that's wind shear. Depending on the Richardson number, this layer might become dynamically unstable. If there's enough wind shear to overcome the static stability of that layer, you'll get these production of these eddies that have rising and sinking motion associated with them. On one side, each eddy is rising motion, and on the other side of each eddy, there is sinking motion. Clouds form where there's rising motion. Clear areas are where there's sinking motion, and when you actually start examining this cloud layer, you can see how, you can actually kind of even envision each place where there's sort of that cloud structure, picture it that that's where the rising motion is, and then there's sinking motion, kind of picture like these rolls of air motion caused by that wind shear here. This is a particular type of cloud called altocumulus. Even atmospheric scientist majors would often look at this picture and say, oh, this layer of the atmosphere where these altocumulus clouds are forming, it must be statically unstable because we get these little rising motions. No, if it were statically unstable here, once we lifted these air parcels, they would keep rising on their own and they'd go all the way to the top of the troposphere. Clearly, this is statically stable. The air is resisting rising, but not resisting rising enough that the wind shear can't overcome it and produce these little rolling motions, which we can see by the rising motion on one side producing condensation and cloud formation, and the sinking motion on the other producing clear sky. That is so cool. That is an important thing. And like I said, there's actually a number of different types of clouds that are formed that way through dynamic instability as there is wind shear between, say, the jet stream and slightly weaker winds below the jet stream. Or, well, any place with wind shear. This is another good example, by the way. These kind of waves that look a little bit like ocean waves, that kind of look like they're breaking on that cloud deck right there, that's called a Kelvin-Helmholtz wave. Again, you don't need to know that term, but they work that way too, as we change the Richardson number of a layer by producing more or less wind shear. or changing the static stability of a layer, the atmosphere adjusts through the process of producing these waves in the atmosphere, these Kelvin-Helmholtz waves. They're going to be, in general, too high to have a direct impact on wind power. I happen to have this picture in my collection of things I've saved over the years with these very low-level Kelvin-Helmholtz waves, but even they would be higher than the height of like a hub of a wind turbine. Another way in which these production of turbulence is very important has to do with the flux of sensible heat and the flux of latent heat at the surface. Let's make sure we review that term real quick. Remember, a flux is stuff, in this case sensible heat, passing through a square meter per second. Sensible heat being like the kind of heat that you can measure with a thermometer. Heat passing through a surface per second, that's really another way of saying conduction. Conduction between the warm ground and the cooler atmosphere above it. Flux of latent heat is the same sort of idea, but it's about the transfer of latent heat through a square meter of the ground per second. Latent heat is like the heat that's absorbed by evaporation. And so when we talk about flux of latent heat in the atmosphere, we're talking about the rate of evaporation off of the surface. All else being equal, these fluxes, that is the rate of conduction and the rate of evaporation at the surface, are going to be much greater if the flow is turbulent than if the flow is laminar. Okay, we're not going to get into the whole business of like why that is and the parameterizations of that and so on. I thought about doing it, but I think that's not directly enough related to the kinds of things someone in a wind energy is interested in. But broadly speaking, at the same temperature, at the same pressure, with the same mean wind speed, having the flow be turbulent will produce more evaporation than if the flow is laminar. It'll produce more conduction of heat between the surface and the atmosphere than if the flow is laminar as well. Cool! That is 3 of dozens of reasons why turbulence is important to the Earth's atmosphere, but they're 3 that touch on things that we have seen or will see yet to come in the book. Alright, now we're just about done with this lecture. Let's answer a couple quick questions before you move on to the next lecture. Question 7. Over long periods of time, turbulence in the atmosphere produces wear on the moving parts of a wind turbine. Is that true or false? We gotta think about turbulent load for a little bit here. Alright. Make a choice from those 2 options and get a little feedback before you move on to question 8.